Hello. Uh, I hope you can hear me. Uh, can somebody confirm?
Yeah, I can hear.
Okay. Wait. Uh, Let me just maybe wait for a few minutes before starting. Start at 10:10. I think, yeah, many of you had also joined the Sunday session, but I'm sorry, I couldn't take it because of network issues on campus. And yeah, hopefully, um, yeah, so that's why I had to keep this session today. But yeah, going forward, it should be the usual time, Sundays 3 to 5 p.m. Yeah, it's kind of fine. I think I can start. Yeah, since if the others join in later, I'll add. So, any questions from your side? So today I'll discuss about um, trading, and so this is content of week 4. Somebody doctor. So regarding content of week 4, does anybody have any doubts? We can then talk about that first, and then can discuss problems also. Okay. Okay. Uh, okay. So uh, there are no questions from your side. Let me try and solve some typical questions that we can anticipate. So, uh, one second. Yeah. Um, let's see. Okay. So let's say the one kind of question here is hmm, how do I put this? Let's say you are given some kind of constellation diagram. Let's say it is something like pi by 4 minus QPSK. Let me pull up the diagram for it. Um, and I- yeah. So, one second. What happened? Uh, I think there was some issue. Let me uh, fix that. Uh, okay. Yeah. let's say you have some, I think this must be known from digital communication. So you have a pi by 4 QPSK constellation, which somewhat looks like this. Uh, you have the real axis. This is the real axis, and this is the imaginary axis on the complex plane. And you have 4 points, right? This, this, and this. So these are kind of at 45-degree angle, minus 45. This is 135, and this is minus 1. Pi by 4, minus pi by 4, 3 pi by 4, and this is minus 3 pi by 4, right? So these are the 4 signals that you have. And you are told that uh, there is no noise. There is no noise, and there are some because there is some user which is transmitting these symbols, pi by 4 QPSK symbols over the channel. There is no noise, and there is some Doppler fading, Doppler impairment, right? Which means that uh, this is the phenomenon of Doppler shift, which happens because of relativity, right? Because of speed of light and like especially for high speed moving uh, high speed moving objects, this is what happens. And so so how will the so this is the original transmitted symbol, let's say. This is the transmitted symbol, right? So how will the received symbol look like? So you are asked, how will the received symbol look like? So and by this I don't mean that receive symbol at a specific instance, but let's say you are recording traces over a long period of time, and then you are kind of plotting all of the received symbols. Um, you're plotting all of the received symbols, and then you are showing me the plot. So how will the received symbol plot look like? Um, okay, so we guide you through this. There are two components in a complex signal, right? You have magnitude, magnitude, and you have phase, right? For any complex number z, it can be represented as mod z e to the power j argument of z, right? Something like this. This is on right? Basic complex numbers. So, which of like if there is no noise, no shadowing, nothing of that, but let me just be specific, no shadowing, no that. It's just yeah. The Wi-Fi is fine. So there is no noise. It's just Doppler impairment. So how? So this is, let's say, the Z transmitted symbol, right? So I denote it as ZT. And then, so what I'm asking you is I'm asking you about ZR, right? The received signal. So this will also be some modulo of ZR, e to the power j, arch, ZR. So, uh, so to answer this question, firstly, do we know the relation between mod ZR? So first, maybe let's figure out the magnitude first, right? Do we know the relation between mod ZR and mod ZT? Uh, so there is no noise, no shadowing, uh, but there are Doppler impairments. So the question is, does Doppler impairment affect the noise, affect the magnitude? Does anybody have an answer? Does Doppler effect affect the magnitude of the signal? I hope you understood, right? Like, so let me just uh, do I need to explain Doppler effect? Is everybody aware of Doppler effect, or should I explain? Um, any, so okay. So Doppler effect is when you have a mobile user, let's say some car, so, not a great artist, but yeah, you have a car, whatever, and you have a passenger inside the car, right? Just taking a typical case, and it is moving along uh, at a speed v, let's say on a road, right? And you have your base station somewhere here, let's say in 2D plane. So, uh, so the signal travels at the speed of light, c. Electromagnetic radiation travels at the speed of light, c. Right? But the person is moving as well. The source is moving. So, so that let's say this angle at any point at the snapshot that I've taken, let's say this angle is theta. So, what is the component of the velocity of the source in the direction of the radiation? Can somebody tell me? So, if I drop a perpendicular, uh, yes, I will conduct it from 6 to 8 p.m. Wait, no, 3 to 5. I won't be conducting this session typically on Fridays. I'll be sticking to my schedule slot, which is Sunday 3 to 5 p.m. And that is what I've promised to NPTL, and that is what works for me. And I cannot change that. And I actually am not allowed to change it once I've committed to it, and I plan my work and my other engagements around it. So I cannot change it, but I believe the other two TAs are taking theirs uh, in the evenings, or according to their availability. So they are taking their sessions on Monday and Tuesday, I believe, in the evenings. So if that time suits you, so that is why we have three different slots, so that you know we understand this is a big course. Different people have different schedules, so you can join whichever session suits your schedule. So if my Sunday session suits your schedule, you can join. You can join the other sessions, and we'll roughly be covering the same content. So it's kind of equivalent. So yeah, I'm sorry, I cannot adjust. Even if I want to, even if I have some emergency or I have something urgent and it would help my schedule if I want to change the slot, I am not allowed to. It's very rigid. So yeah, it's what it is. Uh, so yes, I'm sorry. But okay, let's coming back to this. So you have a mobile user uh, moving at a velocity v, and so what is the component of this velocity in the direction of transmission? Can somebody tell me? So v cos theta, right? So so that is how the Doppler velocity, the Doppler frequency is calculated, or the Doppler shift is calculated. It is the carrier frequency fc times the velocity in the component of the direction v cos theta in the component of the component of the velocity in the direction of transmission, which is v cos theta by c, right? So this is what happens. So the frequency of the signal is increased or decreased by this value, right? So the effective frequency becomes something like so. How does this signal look like? How does this argument part look like typically? So when so typically in electromagnetic waves, you will have the magnitude part, and then the argument part will look something like e to the power j 2 pi f t, right? 2 pi f t, where uh, 2 pi f c t, where f c is here, f c is carrier frequency, right? F c is carrier frequency. And so what this Doppler effect does is it introduces an additional phase shift. So on top of this e to the power j 2 pi fct, you will have an e to the power j 2 pi f dt as well, right? So this is the key kind of concept. But there will only be a phase shift. So this is a phase shift, right? Like this is just a change in the argument part, no change in magnitude. So if I write no change in magnitude. So this is not some kind of fading or anything. This is essentially just a shift in phase. So, so if there is a shift, if there is no change in magnitude, it means that we will essentially receive something very similar to this. So at least having the same radial distance from the origin. But since there will be phase shifts, it will be rotated circularly, right? I hope it makes sense. So your magnitude stays the same and your phase changes. So it will essentially, so no magnitude, so I'm just writing that down. Therefore, this is circular rotation about the origin, about origin. So this is the key concept here. So then here your receipt symbol will it might look like this, it might look like this, it might look like this, whatever, but it will essentially have the same distance from origin. So if you kind of add them all up, or like cumulatively, if you want to show them in a graph, it would essentially be something like, yeah, like you will have circular shifts on all of the four original symbols and in a symmetric manner, right? It's as if you're moving the whole thing around the origin, like you're rotating it around the origin. So this is how your symbol will typically look like at roughly this, at exactly the same distance from the origin, but rotated. And if you add up all these rotations, you will kind of get a circular arc. I hope this makes sense. And this will change. So now if I add more complications, if I add, let's say, noise, and then there is fading, and then there is shadowing, all of these things. So this affects the magnitude. So all of these things impact magnitude, right? Interference, whatever. So all of these things impact the magnitude. And so in that situation, your magnitude won't stay the same. And so you might, in some cases, if there is a deep fade, you might get something like this, very small magnitude. Sometimes, in some extraordinary cases, you might even have some kind of gains. So, like sometimes it's possible, correlated gains and things like that. So, uh, overall, essentially, so this was your original symbol. And then you will have shifts in magnitude as well as, so you will have something like some kind of dotted cloud over here. And similarly, like everything also. Yeah. So I hope this makes sense. Uh, Similarly now, uh, um, yeah. So, okay. So I have not mentioned Doppler here. So that is why I haven't shown any phase shift predominantly. It's actually, yeah, my bad. I haven't mentioned Doppler here. So if there is uh, my bad. So even without Doppler, yeah, if there is fading and shadowing, then there can be some phase shift. So this is how it will look. But if there is a Doppler as well, so if I add, let's say if I add Doppler, so what Doppler does is the phase shifts become significant. So you will have a lot more, especially with high Doppler, with high speed vehicles, then you have a lot more phase shifts. So your symbols are all over the place. Um, I hope this discussion was clear, um, and you get an idea. Okay. So the second question, like kind of second type of question that you can get, uh, is that you are given some kind of plot, like um, yeah, let's say you're given some kind of plot like this. You have kind of so this is, let's say, amplitude. Like so you have a channel. You have a channel which is with I'm denoting by H, and this is a complex channel. In the frequency domain, it has a certain impulse response, right? So you are denoting it as H of n. So this is the impulse response of channel. Uh, so I'll just denote it as. So what you are plotting is essentially the modulus of the impulse response versus the time elapsed versus like time resolution. Uh, that's kind of like how far you are going. So you have three different, let's say, this one is curve number A, right, which is static somewhat. Then you have a slightly wiggly curve. So this is B. And then you have a very, very oscillating curve, which is C. I don't have color, so I'm not being able to do a great job, I guess. But let me just make a small legend. So the most static line is A, the slightly wiggly line is B, uh, and the very this line is C. So all of them oscillate or kind of have the same mean. All of these three lines. In that, I'm not being able to do a good job. I hope you get the point. So all of them are having roughly the same mean, but their fluctuations are different, right? So this means that theoretically, this means that typically the large scale, so there are two kinds of fading, right? Large scale fading, which is essentially typically which is path loss plus shadowing. So This is the same. This is the same for all three. So what is different is the small scale fading difference, right? So that's how you theoretically understand it. Small scale fading is different. It's different. So so the question is that uh the order, let's say order in increasing or like right in increasing order of coherence bandwidth. Okay. So right in increasing order of coherence bandwidth. Okay. Uh, so how do you solve for this? A second. Uh, so what do you mean by coherence bandwidth? Uh, that you mean that you are trying to capture the like fluctuations in the signals, right? And so your uh, question is that like by coherence bandwidth, what we mean is um, how high does the frequency of like loosely speaking, how high does the frequency of sampling have to be able to capture the signal appropriately? So this is a time varying impulse response of the channel. So how fast do I need to sample so that I can actually capture the behavior of the channel properly, right? So higher the so essentially higher uh, coherence bandwidth, coherence frequency, or like indicates essentially faster sampling, which typically indicates like fast fading, right? Fast fading. So the channel is definitely fluctuating a lot more. So you really have to sample at smaller intervals of time so that you can capture the channel better. Uh, I think second. Sorry. I shouldn't write it this way. I should write directly that high fluctuations imply that you have to sample faster. So and so fluctuations. This is referred to as fast fading actually. So so you will have to sample faster and and then which means that time resolution or like time resolution is small, right? You really have to sample at smaller intervals of time. So, uh, and then the coherence bandwidth B is actually inversely proportional to this time resolution. Let's denote it as B. Why? Because so higher the coherence bandwidth, that means we have a more flat fading or a like sorry a slow fading channel, right? Which means that the channel is more or less like constant for a bigger duration of time. So um, So in increasing order of coherence bandwidth, so this order will be opposite of the time resolution order. So according to time resolution, so according to T, it's clear that C is fluctuating the fastest. So I have to measure T a lot quicker than I have to measure the signal C faster than I measure the signal B, faster than I measure the signal A. Because A is fluctuating slowly, I can afford to measure A at longer intervals of time. At longer intervals of time. But when I talk about coherence bandwidth, um, the answer flips because I'm trying to see for for it's just the opposite relation actually that for how much frequency am I being able to assume that the channel is roughly constant, that the channel is not changing. Uh, so for that actually I need to flip the order, and so it will be A less than B less than C. So these kind of tricks are there. So you need to carefully check the question whether they are asking about time order, time resolution order, or coherence bandwidth order. So um, so yeah, this will be the correct answer because yeah, this will be the correct answer. Is this clear? So essentially, it's like um, in time domain, if you have a DC signal, it means that its frequency is zero, right? So all of the magnitude is concentrated at frequency zero. So it's a less fluctuating signal. But then when you have more fluctuations than or fluctuation with a higher frequency, that means you have a frequency spectrum of that signal now. So you have a higher bandwidth of the signal then because you have all tones from low to high frequency, and so you have to cover the whole area. So you have a higher bandwidth now. And so by similar logic, if you have a faster fading channel, if channel is fluctuating faster, then your time resolution has to be low. You have to sample at a faster intervals of time. You have to take channel estimates faster, and then so if you draw impulse response, your channel is fluctuating fast, so you will have like high frequency. Actually, this is amplitude, so I should not have written it as this. This is time varying channel response actually. So this was my mistake. I'm sorry. But yeah, like time varying response in this. So if you have like faster fluctuations, it means in frequency you will have high frequency signals, and so higher frequency signals, and so your bandwidth increases. Um, so it's just the opposite relation. I hope this is clear. If there is any doubt, I can ask. This is a big conceptually. And I think the other question is directly from the slides, so I'll skip it. Like in the third question in your assignment, or I don't think I should cover it because it's directly there in your slides, and you can get it out. Okay, so um, any questions so far? See. Okay. Uh, Fine. Let's go to the third type of question. So, so you are given like some kind of fading channel. Um, so your received signal is some kind of HS plus N, right? Yeah. So so what does this look like? You have a transmitter, you have a receiver, X, RX. Well, I don't need to draw. I hope it's clear, right? You have a single channel, you have a simple channel. So, so this is your received signal in the frequency domain. Your received signal is this is a transmit symbol S and the fading coefficient H. So maybe let's write that down. R is RX symbol. S is uh, TX symbol, right? TX symbol. And then you have H fading, that this is the fading coefficient. And then N is noise. Right? This is like typical model of some kind of channel. And you are told that H, the fading coefficient, is distributed as complex normal with mean 0 and variance 1. Let's say. Or let's just change it. Variance is like 1 is fine. Let's do 1. Let's do 1. So you are told that find right. So your signal is transmitted at so okay. Let me just write the question first. Find probability that let's say Rx power is less than Rx power is uh, less than like maybe 10 dB below uh, is is sorry is greater than 10 dB smaller than um, the mean Rx power. So this is your question. You're told that like so what does this what is the key question, concept that this question rests on? The key concept here is that your channel model is fading channel model. So you don't really know the exact channel at any time. All you know is a statistical distribution. Unless you measure the channel, you won't know the channel, and so you cannot predict properties in advance. But you know some degree. You know to some degree, you know a statistical distribution of the channel, and we are trying to see what is the probability that like we have some estimate of the mean, so we know the mean statistics of the receipt power, and we are trying to see the probability that we'll get receipt power that is 10 dB inferior to the mean, that we'll get something 10 dB poorer. So like that is like a bad or unwanted scenario which we don't want. So we are trying to see what is the probability that that situation will happen, right? So uh, so let us then calculate the mean receipt power. Right? So the mean receipt power is nothing but expectation of R squared mod or modulo R squared. And that will be, so we know that the symbol and the fading and the noise, they are independent of each other, right? So if they are independent of each other, which means that they are uncorrelated, and so I can simply add their magnitudes, right? So I'll just have mod h square, then expectation of signal square plus expectation of n square. Right? Something like this. Because the cross term will just go to 0. The cross term will just go to 0. Okay. Uh, so this is the mean received power, and so okay, I should, yeah, I'll also take an expectation over this fellow, the feeding channel. So this will be nothing but so we know that H is complex normal 0, comma 1. So I can just put it over here, and so what I'll get is expectation of S square plus expectation of N square, right? This is my mean received power, and so the actual received power, which is mod R square, is just if you remove the expectation over the fading, then the rest stays the same, right? So you will have mod H square, expectation of mod H square plus expectation of mod N square. And so what I want here is that the probability that right, probability that this thing mod R square uh, is less than expectation of mod R square divided by is less than this value by a magnitude of 10 dB, right? So it's even worse. So that is why I have the less than sign here, because we needed it to be below, like below 10 dB, 10 dB or even below. So that is why I have a less than sign here. And 10 dB in dB scale, which means in linear scale it will be 0.1 times 10 to the power 10 divided by 10. Um, or yeah, my bad, sorry. It should be 10 to the power 0.1 times the dB value, which is 10. In linear scale, this is actually equal to 0.1 times 10. So this is actually equal to 10. So I need something that is 10 times worse. I want to see the probability that it is 10 times worse. This, I hope this conversion makes sense, right? So I'm just by 10 dB smaller, if I'm comparing in linear scale, it means it is by in multiplicative sign, it is 10 times worse. So I need this probability. So if I just do some simplification over here, right? So actually, I have made a mistake here. So this part is actually not the received signal power. This is the noise power. This is the noise power, right? So I shouldn't consider the noise power in the signal power. So let's not talk about the noise power from now. And so this is just a signal power. So in signal power, you will just have the signal component, which is fading times the signal. So so that is why this change is there. And what we can do is to account for the noise, we can just normalize it by the noise power. So we can just normalize the signal power by the noise power, so that the other part, the noise power, is equivalent to 1. So this is something that we can do. And we can denote this part, this as some gamma, expectation of normalized kind of SNR, if I may call it. So we call this as gamma. So if I just substitute, then what I have is, so this is equal to gamma. because expectation of mod h square is 1, and this is equal to, this is essentially mod r square equal to mod h square times gamma. And so I need the probability that mod x squared times this quantity gamma is less than gamma divided by 10, right? So I need the fading, and so if gamma cancels out here, so what I will have is probability mod h square being less than 0.1. So the original, the actual transmitted signal power becomes immaterial here for this problem, because I just want to see what is the probability that I will be 10 dB worse than the mean. So whatever be the mean, then that kind of normalizes out, right? I just want to see if I, what is the probability that I will be in some kind of bad situation, 10 dB below the mean. So now it all depends on this, the distribution of this mod h square. And we know that h is complex normal 0, 1. And so from basic probability statistics, actually we can say that mod h square will then be an exponential random variable with mean 1. Or yeah, an exponential random variable with mean 1. So essentially, so the, so if I denote this mod h square by some quantity x, then x follows. So then like f of this, the PDF is e to the power minus x for x greater than 0, right? So I just need to then solve for probability. So if I integrate the PDF, so what will I get? If I integrate the PDF from 0, because this is exponential variable, starts at 0 and integrate till 0.1. So I'll get, I think, 1 minus e to the power minus 0.1, something like that. So whatever is the value. So this is the probability that, yeah, so somebody can calculate the value and tell me, but conceptually, this is the idea. This was an important question. If somebody has doubt, they should ask me. And so in a very similar notion, let's say in the same question, for everything, every other thing same, you are asked directly that find the probability of deep field. Deep field. So this is also a technical term that you need to understand, and it follows from the same concept. So what do we mean by deep field? Can anybody tell me? What do we mean by deep field? So by deep field, what we typically mean is this signal power. So signal power here is essentially signal power going below the noise floor or the noise power itself. So this is when you call this situation as deep field. Or if I have to write it this way in terms of gamma, so gamma is nothing but PS by Pn, signal power by noise power, or expectation of mod S square over expectation of mod N square. So this now becomes less than 1 in linear scale. And in dB scale, this becomes, so gamma dB, this becomes less than 0 dB, right? I'll denote this as gamma effective after this. Yeah. So gamma dB less than 0 dB, this kind of situation, right? 1 second. So, so what is the received signal power? Like gamma, let me not write this one because it's confusing with the previous problem. So gamma received is signal per received divided by noise per received. This is less than 1. So gamma received has to be less than 0 dB, right? So what is this gamma received here? So the received signal power is the gamma received signal power is mod h squared times the transmitted signal power, right? And whatever is the transmitted signal power. And for deep fade, we need this to be less than 0 dB in decibels, in like in the log scale. In linear scale, it has to be less than 1. So I need to find probability that mod h squared is less than 1 by gamma t transmitted SNR. So that is all. And so now, again, if I assume an exponential random variable, so that will be e to the power minus x dx integrated over 0 to 1 upon gamma transmitted. So this is the probability of deep field. So this is probability of deep field. And you can do the rest of the calculation depending on values provided in question and so on and so forth. So that I hope this is clear. You yeah, I hope this is clear. Any doubts, any questions? Okay. So for this this exercise or this kind of problems, sometimes you are asked to provide like high SNR or low SNR approximations, right? Assume there is high SNR, what is the approximate value of so and so quantity? So this is nothing but basic uh, Taylor series expansion. So, so wherever, let's say for this question itself, probability of deep fade, here the exact answer will be, to solve it, it will be 1 minus e to the power minus 1 by gamma transmitted, right? Let me just simply write it down. So you need to, let's say you are said that gamma is high, so high SNR regime, you are in high SNR regime. So how will you approximate it? So you just need to know, or you need to derive like the Taylor series expansions, some common one they should know. So for e to the power, so you just need to use these formulas essentially, something like 1 second. So for e to the power minus x, this is approximately equal to 1 minus x plus x squared by 2 factorial. You don't need to go further. Typically, a linear approximation minus dot 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 whatever. Typically, a linear approximation is good enough. So if you have, if x is small, so this is like an exact equality. And if x is small, so then the higher the exponent value, the smaller the value of the term, right? So you will typically write it as a linear expression for x uh, x small, right? So you need to use this kind of approximation. And so for high SNR, so if gamma is high, it means that this 1 by gamma is low, right? So that means this will come in the small x approximation, and you can use a linear approximation and derive the result, final answer. So that kind of idea, very basic, elementary algebra. So, uh, so this is one kind of motion. Then, uh, if this is clear, then I'll discuss something else like uh, bit error, symbol error, things like that. But first, is this clear? Any other questions? Any questions? Any doubts? We are discussing about fading, so maybe I'll just complete that uh, discussion also. So there are some questions about fading margins, and you are given a plot in Gaussian distribution. So it's just you have to interpret the graph. That's all. I think it's question 14 in your assignment, and it's also discussed in the lecture. It's you don't have to do any calculation. You just have to see the graph and see, you know, what where the graphs are intersecting and what is what margin you should provide so that you are guaranteed to have an outage probability less than a certain value. So you can just do that. I don't think it's too deep conceptually. Can we get the model question of final exam? I am not the authority to decide on that, to give that. I'm no authority really. Um, I do discuss with the course instructor sometimes, but so everything is up to him. If he if he wishes to provide a model question paper, he can, or he might not. And you already have assignments and quizzes, and the whole point of these assignments is to help you prepare. Firstly, understand the course content, and also help you prepare for the exam, because your exams will typically have material that is similar to the assignments. Um, so if you, and I think it's safe to assume that you might not get a model question paper fully, but if you do the assignments, if you understand the concepts and the way they are covered in the assignments, you should be well prepared for the exam. You don't need to do anything else. At least that's what I have done in my coursework at IIT. That's typically how it works out. So this was one kind of concept that I had to cover, and I think people are dropping off. Okay. So now on similar lines, like there, let's say, fourth kind of question. So you are asked many questions about the Raishian and Nakagami M fading and all that. So these are mostly textbook questions, but let's still discuss. Uh, okay, it's fine. So how does a Raishian channel look? So a Raishian channel, so it's Raishian, the way it is modeled is. So you have some kind of uh, this factor, right? Raishian factor root over kappa, let's say, times the line of sight component of the channel plus, uh, uh, sorry, it's not like this, it's something like root over kappa by 1 plus kappa plus, so this is the Raishian channel model, K. let me denote this as K, not that. Okay. So this K is known as the Rician K factor. And so, and the both of typically we have mod HLOS is equal to mod HNLOS. So the line of sight and non-line of sight components are modeled with the same kind of complex distribution. But then you have these factors, pre-multiplied factors. And so in this kind of model, typically the ratio of the line of sight power of the signal. So you have a channel and you have a line of sight component, you have a non-line of sight component. And the ratio of the power of the magnitude of the square of the magnitude of line of sight component and non-line of sight component is K. So this is the bottom line. This is the ratio of the line of sight and the non-line of sight component, right? So let's say you are told that in a certain environment, the channel is becoming let's say you're told channel is becoming not NLOS, or essentially you're told that the power of the non-line of sight element is increasing, right? When does this happen? Let's say you have a line of sight channel and there is some kind of obstacle in the line of sight channel, like you have maybe a tree in between. You have a pedestrian here. You have a base station here. Some kind of tall base station is here. But then you also have, let's say, a tree, some kind of obstacle in between. So this is your line of sight path, right? And then this gets obstructed because of the tree. Because let's say you've moved too close. So then your channel's non-line of sight character is increasing. So in that case, what will happen to your Rician factor? How will the Rician factor change? It's very obvious that your NLOS component, if it increases, then this Rician factor comes down, right? So this is one key kind of question that you can get. You can be told that your channel becomes more line of sight in nature, less line of sight, NLOS power is increasing, something or the other. And all you need to know is you have to use this ratio. That Rician factor is ratio of line of sight component power divided by non-line of sight component power. And you can solve those kind of questions. And extreme case, okay, let's say your channel is pure NLOS. Now you are told that your channel is pure NLOS or pure line of sight, right? Pure line of sight channel. You have no NLOS component, no scattering in the environment. You are, let's say, operating at terahertz frequencies or something like that, very high frequencies. So there is almost negligible, no NLOS component. Then what is the value of K? So for pure line of sight channel, what is the value of K? So in a pure line of sight channel, what is the value of non-line of sight component power? Can somebody tell me? It's pure line of sight, so there is no NLOS component. What is the value of non-line of sight power? It's approaching zero, right? It's like next to negligible. So we'll have, obviously, then we'll have, if the denominator is approaching zero and numerator is finite, we'll have K approaching infinity. So this is one extreme case. And the other extreme is, of course, pure NLOS channel where K is zero. So, so this kind of concepts are there. And so for yeah, so this is generalized form of fading. And so if you want pure NLOS channel, so this essentially then becomes a Rayleigh fading channel. So Rayleigh fading distribution is designed for predominantly or pure NLOS channel. So here you will have your uh, line of sight power going to zero, is equal to zero. And if you put that in here in the ratio, so you'll have Raishon factor equal to zero. And so if you put k equal to zero over here, if you see that you will get h is equal to h NLOS because this term goes to zero. The line of sight term goes to zero. I can write it down. So h equal to h NLOS. So you just have the non-line of sight. So this is like a Rayleigh fading channel. There is no line of sight component. It's fully non-line of sight. Okay. And another important concept, which was told in the lecture, is another kind of fading that is commonly used is the Nakagami M fading. Uh, so where you are modeling H as a this gamma random variable, right? With parameters n comma 1 by n. This uh, this topic, fading channel topic, does involve a lot of probability and statistics. So you have to get used to these. So m here is an integer typically, and there is a rough empirical relation. So m is approximately equal to k plus 1 whole square divided by 2k. So this is the Raishon k factor. So this is relation between Raishon and Nakagami MCD. So if you are given value of k, so like uh, let's say you are told that Raishon factor k for some, this is actually like something that I use in my research also. So you are told by, let's say you are doing some uh, work in your company and you have to follow 3GPP standards. So typically in 3GPP, they will give you the values of the Raishon factor. Typical Raishon factor for a certain scenario, like let's say urban scenario or rural scenario or whatever, macrocellular, microcellular, whatever. So you'll have to use that. So let's say you are told this is like 7 dB. 7 dB, that is linear scale, it should be 10 to the power 0.7, right? So sometimes for purpose of research, uh, on analytical purposes, Nakagami M fading has a nice distribution, and it is analytically more solvable. Like it is sometimes difficult to get like good, nice mathematical expressions with the Raishon channel, and so you sometimes have to resort to Nakagami M channel fading model. And so what you need to do is you need to use this equivalence relation to find the equivalent value of n for this. So can somebody tell me so the question is for k equal to 7 dB, what is the equivalent n, Nakagami n, Nakagami m factor? You just have to use this formula. Can somebody tell me? Let's see. So you just have to put 10 to the power 0.7 plus 1 whole squared divided by 2 into 10 to the power 0.7 plus 1. That's all. So, fine. You can calculate and tell me. So, this is, so you will typically not get an integer value. You will get some decimal and you have to take the nearest integer. That's how you have to do. You can take like essentially this is one key that m has to be integer. So can somebody tell me to calculate it? Yes. Yeah. Uh, yeah, that's good. Don't have my calculator nearby, so fine. And, using Google calculator. Plus one. So yes, I think for me it's coming out to be roughly 3.28. And so when I will put Nakakami, when I will use the Nakakami M shading, I'll just round it off to something like 3. Okay. Uh, okay. Uh, what else? Any other questions? Or this is all mostly I think I've covered shading issues. Uh, Another key component is this notion of uh, sorry, BER, right, or bit error rate. So this stands for bit error rate, and then you have SER, which is symbol error rate, right? So, so this is that, right? So a very simple question can be that you have in a channel you are told that uh, bit error rate, symbol error rate, and then error probability result. So this mechanism. So you're told that probability PE is probability that uh, probability of bit. So this is the notation that we told. The probability of bit error is PE. So if you send a bit, then the probability that it will be received in error, you will receive so the wrong bit. If you transmit 0, you will receive 1. If you transmit 1, you will receive 0. It's PE, right? So you are asked probability of um, 3 bits probability of 3 bits received in error. All 3 bits are received in error. Can somebody tell me? So probability that 3 bits are received in error. For a single bit, it is PE. It's just one term. For 3 bits, all 3 of them to be in error, what is the probability? The key concept here is that, like, if you can roughly assume, transmission of every bit is independent. So it's not, so typically in this kind of problem, we'll assume that every bit is transmitted separately, and so it's an independent random trial in a way. So what is the probability that all 3 bits are received in error? So you will have to have first bit in error and the second bit in error and the third bit in error, right? So then what will be the probability? So it's just translating the logic in from words to maths, right? So your first bit has to be error, intersection, second bit, and your second bit has to be in error, and your third bit has to be in error. So all 3 of them have to be in error. Actually, yeah. So this is like all, like I should be very clear, all 3 bits. So I'm told all 3 bits. So this will be PE cube, right? Yeah. Now I'm told that, let's say, let me change this question a bit. Let's say you are transmitting an 8 PSK symbol. 8 PSK symbol. So in an 8 PSK symbol, I'll have like phase shift king. So I have essentially 8 different phases. And so this is essentially 3 bits. We know that 3 bits. So this is 3 bits. And so now I want to find out probability of symbol error. Probability of symbol error. So this question is different. How? Because for the symbol to be in error, I don't necessarily need to have all 3 bits in error. Even if one of the 3 bits is in error, it means my symbol is in error. So a better way to approach is, so essentially probability that, so I can do the 1 minus approach. That makes it a lot more neater. So probability that symbol is an error is 1 minus the probability that symbol is decoded correctly, symbol received correct. I think this using short form here. I hope this is clear, right? So probability of error is 1 minus probability that it is received correctly. And why did I do this? Because it makes it simpler. Now I can see this probability of symbol received correctly. This is so for the symbol to be received correctly, we need all 3 bits to be received correctly. All 3 bits have to be received correctly. And what is the probability? So I'll just write it down. All 3 bits correct, right? And so what is probability of 1 bit correct? Probability of 1 bit being correct? The probability of 1 bit being in error is PE. So what is the probability of 1 bit being correct? Can somebody tell me? This should be simple. It is 1 minus PE. Right? So if the probability of error of single bit is PE, then being correct is 1 minus PE. And so if you need all 3 bits correct, so then this becomes 1 minus PE whole cube. You need all of them to be correct. And so your probability of symbol error is 1 minus probability that symbol is received correctly. So it becomes something like 1 minus P whole cube. So you have to become comfortable with this kind of probability and statistics kind of calculations, probability manipulations and things like that, because this is kind of the heart of this. This is the heart of this kind of topic. So that is nothing there. Now, so we have denoted this PE quantity. Here we have denoted this PE quantity as like we have denoted this probability of bit error as PE, but it has an expression. So let's move on with that. So probability or like this this probability is actually denoted as bit error rate. Bit error rate, and there is a formula for this. It is essentially Q function of square root of SNR. That is the main like kind of, or this is Q function of root over n times E B by n naught. Why? Because SNR is symbol energy, ES. My bad. Apologies. ES by n naught. Symbol power by noise power, right? And so symbol power is nothing but the number of bits per symbol times the energy that you are applying per bit divided by the noise power. And so for an AWGN channel, I should mention this is bit error rate for AWGN, additive white Gaussian noise channel. So this is plain digital communications, just kind of a refresher. So bit error rate for AWGN channel is given by Q function of this square root of SN, right? And so we can use this formula to solve questions now. That this is the exact expression. So for Q function, you cannot really calculate. You have to use Q function tables online or on your calculator or MATLAB, wherever. So this is not something too interested in. Like, so you will typically have questions like for 16 QAM, you are told that EB by N naught is like I don't know 4 dB. Find VER. So this is very simple to calculate. The first step is converting dB. You have to convert dB to linear scale. So 4 dB is nothing but 10 to the power 0.4. So this is linear scale. And for 16 QAM, the number of bits per symbol n is equal to 4. You know this. And so you just have to find BER equal to Q times root over n times VB by n naught. So it's 4 into 10 to the power 0.4. And if you do the calculation, you will get your answer. That is all. And this is like a very put the formula, get the answer kind of question. So this is what we were denoting as PE earlier, right? And so now let's say you are said that so this is the bit error rate. Now if you are asked the symbol error rate, that your symbol is an error. So this will be 1 minus probability that symbol is correct, right? And by the same logic, for symbol to be correct, you need all 4 bits to be correct. So you will have something like all 4 bits to be correct. So you'll have 1 minus P whole to the power 4, right? And so P is, the value of P, you have calculated from here. And so you will just put it here and then you will get your answer. You will get your symbol error. That's all there is. It's very, it's conceptual. It's just formula based. So that is one key concept. Anything else? Okay, any question that you have? Let's see. Most of them are textbook kind of questions. My bad. Just a second. I'm getting a call.